Reinforcement learning. How machines learn from experience. Introduction. In the last episode, we delved into the fascinating world of deep learning, understanding how computers can recognize images, interpret text, and even communicate. Building on that knowledge, today we're going to explore reinforcement learning, a powerful technique that enables machines to learn from their own experiences, much like humans do. Imagine a child learning to ride a bicycle. At first, the child might wobble and fall, but with each attempt, they gradually learn to balance better. This process of trial and error, combined with feedback, like staying upright longer or getting praise from a parent, helps the child improve over time. Reinforcement learning mimics this process. It teaches algorithms to make better decisions by trying different actions and learning from the results, whether those results are successes or failures. What is reinforcement learning? Reinforcement learning is a method where an algorithm learns to make decisions by receiving feedback in the form of rewards or penalties. This is similar to how humans learn, by trying different things and seeing what works best. Think of it as playing a game. The player, in this case the algorithm, tries out different strategies. If a strategy works, the player gets points and continues. If it doesn't work, they might lose points or have to try again. Over time, the algorithm's goal is to figure out which actions lead to the best outcomes. It learns by exploring different possibilities and gradually improves at making the right choices, just as a person might improve at playing a game or solving a puzzle. Deep dive into how reinforcement learning works. Let's imagine a simple example. A robot trying to navigate a maze. At first, the robot doesn't know where the exit is, so it explores the maze randomly. Each time it hits a wall or a dead end, it receives a penalty. Maybe its battery drains a little, but when it moves closer to the exit, it receives a reward. Perhaps its battery gets a boost. The robot starts by trying out different paths. When it finds a path that brings it closer to the exit, it remembers that path as a good choice. If it hits a dead end, it remembers that as well, and tries to avoid it in the future. Over time, after many attempts, the robot learns the best path to take to escape the maze quickly. This learning process is guided by two simple principles: rewards and penalties. A reward is a positive signal, like finding the right path in the maze. A penalty is a negative signal, like hitting a dead end. The algorithm's goal is to maximize its rewards and minimize its penalties, which helps it find the best solution to the problem it's trying to solve. Now, let's break down the process into more detailed steps to understand how reinforcement learning actually works. The environment. This is the world in which the algorithm operates. It could be a maze, a video game, or even the stock market. The environment provides the context for the algorithm's actions. The agent. This is the algorithm itself. The agent interacts with the environment, making decisions and taking actions based on its current state. States. A state represents a specific situation in the environment. For example, in our maze example, a state could be the robot's position in the maze at any given time. Actions. These are the choices the agent can make. In the maze, actions might include moving forward, turning left, or turning right. Rewards. After taking an action, the agent receives feedback from the environment in the form of a reward or a penalty. This feedback helps the agent learn which actions are good and which are bad. Policy. A policy is a strategy that the agent follows to decide which action to take in each state. The policy is what the agent is trying to improve over time. Value function. This function estimates the total amount of reward an agent can expect to accumulate from a given state. It helps the agent decide which actions will likely lead to the best outcomes in the long run. Exploration versus exploitation. A key challenge in reinforcement learning is balancing the need to explore new possibilities, exploration, with the need to stick with what has already been learned. Exploitation. Exploration versus exploitation. Let's dive deeper into this critical aspect of reinforcement learning. Imagine you're in a new city and you're hungry. You have two choices. You can either go to a restaurant you've been to before and know is good, exploitation, or you can try a new place that might be even better, exploration. This is the same dilemma an algorithm faces. If it spends too much time exploring new options, it might miss out on consistently good choices it already knows. But if it only sticks to what it knows, it might never discover something better. In reinforcement learning, the algorithm has to find the right balance between exploring new possibilities and sticking with the strategies that have worked well so far. This balance is crucial, because if the algorithm explores too much, it may waste time and resources on unproductive paths. On the other hand, if it exploits too much, it might miss out on better solutions that could lead to higher rewards in the future. Simple reinforcement learning algorithms. Now that we understand the basic concepts, Let's explore some simple yet powerful algorithms that use these principles. Q. Learning. Imagine you have a map that shows the best move to make in any situation. Q-learning is an algorithm that builds this map by trying different actions and seeing what rewards it gets. Over time, it learns which actions lead to the best results, and the map becomes more accurate. Q-learning works by updating the expected rewards for each action in each state. For example, if the robot in our maze finds a path that consistently leads to the exit, Q-learning updates the Q value for each step in that path, reinforcing the idea that these are good actions to take. This allows the robot to quickly identify and stick to the best path in future attempts. SARSA. SARSA is similar to Q-learning but with a slight difference. Instead of only learning from the rewards it gets, SARSA also considers what might have happened if it had made a different choice. This helps the algorithm learn to avoid risky moves and make safer decisions. For instance, if the robot in the maze had the option to turn left or right, and turning left led to a dead end, while turning right led to the exit, SARSA would factor in the potential outcome of both actions. By considering what could have happened, SARSA helps the robot make better decisions in situations where the best choice isn't immediately obvious. Monte Carlo methods. Another approach is the Monte Carlo method, which is used to solve problems by running many simulations and averaging the results. In the context of reinforcement learning, Monte Carlo methods involve the agent learning by averaging the rewards it receives over multiple episodes, rather than updating its knowledge after each individual action. This method is particularly useful when dealing with complex environments where the agent's actions have long-term consequences. Real-world applications of reinforcement learning. Reinforcement learning is not just a theoretical concept. It's used in a wide range of real-world applications that make a significant impact on our daily lives. Let's explore some of these applications in detail. Video games. One of the most well-known uses of reinforcement learning is in developing artificial intelligence for video games. Algorithms like AlphaGo, developed by DeepMind, have been able to defeat world champions in complex games like Go by learning strategies from millions of simulated games. The algorithm learned to anticipate and counter human strategies, making it an incredibly powerful opponent. This technology isn't just limited to traditional board games. It's also used in video games to create more intelligent and adaptive non-player characters, NPCs, that can learn from players' actions and provide a more challenging and engaging gaming experience. For instance, in real-time strategy games, AI-controlled opponents can learn to adapt to the player's strategies, creating a more dynamic and unpredictable gaming environment. Autonomous robots. Reinforcement learning is key in developing robots that can navigate unfamiliar environments or perform complex tasks, such as cleaning a room or assembling products in a factory. For example, a robot vacuum cleaner uses reinforcement learning to map out a room, avoid obstacles, and optimize its cleaning path over time. In industrial settings, robots use reinforcement learning to perform tasks like welding, painting, and assembly. These robots learn to improve their accuracy and efficiency by receiving feedback from their environment, such as the precision of a weld or the quality of a painted surface, and adjusting their actions accordingly. Self-driving cars. Self-driving cars are one of the most exciting applications of reinforcement learning. These vehicles use reinforcement learning to make real-time decisions, such as when to accelerate, brake, or change lanes. For example, when a car detects an obstacle, it must quickly decide whether to brake, steer around it, or continue driving. Reinforcement learning helps the car learn from these situations and improve its decision-making over time. In addition to basic driving tasks, self-driving cars use reinforcement learning to optimize routes, reduce fuel consumption, and improve passenger comfort. The car's AI constantly analyzes data from sensors, cameras, and other sources to make split-second decisions that ensure safety and efficiency. Healthcare. In the medical field, reinforcement learning is being used to develop personalized treatment plans for patients. For example, an AI system might learn to adjust a patient's medication dosage based on their individual response to treatment, aiming to maximize the effectiveness of the therapy while minimizing side effects. By continually learning from patient outcomes, these systems can provide more accurate and effective care. Reinforcement learning is also used in medical imaging, where AI algorithms learn to identify patterns in scans that indicate the presence of diseases like cancer. Over time, these systems become more accurate in detecting early signs of illness, leading to better outcomes for patients. Finance. In the world of finance, reinforcement learning is used for algorithmic trading, where AI systems learn to buy and sell stocks based on market trends. These systems analyze vast amounts of data in real time, learning to predict market movements and make profitable trades. As the AI continues to learn from its successes and failures, it becomes better at managing risk and maximizing returns. Reinforcement learning is also used in portfolio management, where AI systems learn to allocate assets in a way that balances risk and reward based on an investor's goals and risk tolerance. By continually learning from market conditions and the performance of different assets, these systems can help investors achieve better long-term results. Chatbots and virtual assistants. Advanced chatbots and virtual assistants use reinforcement learning to improve their interactions with users. As they engage in more conversations, they learn to understand user preferences, provide more accurate answers, and even anticipate user needs. For example, a virtual assistant might learn to schedule appointments or make recommendations based on the user's past behavior. In customer service, chatbots use reinforcement learning to handle a wide range of queries, from answering frequently asked questions to resolving complex issues. By learning from each interaction, these systems become more efficient and effective at providing support, reducing the need for human intervention. Challenges in reinforcement learning. While reinforcement learning has enormous potential, it also comes with significant challenges. One of the biggest challenges is that it often requires a lot of data and time. The algorithm needs to try many different strategies before it finds one that works well. In complex environments, this can take a considerable amount of computational power and resources. Another challenge is that rewards can sometimes be hard to define or are too rare. For example, imagine a video game where you only get points if you finish the level. If the level is long and difficult, the algorithm might not receive enough rewards to learn effectively. This is known as the sparse reward problem, where the agent struggles to learn because the feedback it receives is too infrequent. There's also the risk that the algorithm might learn to cheat the system. If the rewards are not well defined, the algorithm might find unexpected ways to achieve the goal that aren't really what you want. For instance, a robot tasked with cleaning a room might learn that it can clean by simply avoiding dirtier areas altogether, rather than actually cleaning them. Additionally, reinforcement learning models can sometimes overfit to the specific environment they were trained in, meaning they may perform well in one scenario, but poorly in another. This lack of generalization can be a significant limitation when deploying these models in real-world applications where conditions can vary widely. The future of reinforcement learning. The future of reinforcement learning is bright and full of exciting possibilities. As computing power increases and access to data grows, these algorithms will become even more efficient and capable. One promising area is combining reinforcement learning with other types of learning, like supervised learning and unsupervised learning, to create hybrid models that learn faster and perform better. For example, an AI system might use supervised learning to quickly learn basic tasks, and then switch to reinforcement learning to fine-tune its performance based on experience. There's also growing interest in developing reinforcement learning algorithms that are safer and more ethical, as these systems are used in more critical applications, such as healthcare and autonomous driving, ensuring that they make decisions that are fair, transparent, and aligned with human values will be crucial. Researchers are also exploring ways to make reinforcement learning more sample efficient, meaning the algorithms can learn from fewer interactions with the environment. This could involve techniques like model-based reinforcement learning, where the agent builds an internal model of the environment to simulate and predict outcomes, reducing the need for costly trial and error in the real world. Quantum computing is another area that could revolutionize reinforcement learning by providing the computational power needed to solve complex problems that are currently beyond the reach of classical computers. This could enable breakthroughs in fields ranging from materials science to artificial intelligence. Conclusion. In this episode, we've explored the fascinating world of reinforcement learning, from its basic principles to its real-world applications and future potential. We've seen how algorithms learn from experience, much like humans do, and how this powerful method is shaping the future of technology. In the next episode, we'll dive into another exciting topic: how artificial intelligence is being used in creative fields like art, music, and writing. We'll explore how machines are learning to create and what that means for the future of creativity. Thank you for joining us on this journey through reinforcement learning. Don't forget to subscribe and hit the notification bell to stay updated with our AI series. See you in the next episode.